Hello, and welcome to Beyond the Last Star. Wherever you are right now, whatever kind of day it has been, you made it here, and that is enough. Find a comfortable position. Let your body settle. If you can, turn the lights down low or off completely. Because tonight, we are not staying here. Tonight we are going somewhere most people never think to go, past the last planet, past the edge of the sun's reach, into the deep and patient dark where the real universe begins. Before we leave though, drop a comment and tell me where in the world you are listening from right now and what time it is there. I read every single one. There is something I love about knowing that people from every corner of this small blue planet are drifting off to the same stars at the same moment. And if this is your first time here, welcome home. Hit subscribe so the next journey finds you. Now, are you ready? Let's go. The universe is older than the word ancient. It is older than any metaphor we have for old. When scientists measure its age, they arrive at a number so large it loses meaning the moment you hear it. 13,800,000,000 years. But here is what that number actually means. It means that light has been travelling since before the Earth existed. It means that somewhere out in the dark right now, photons are still moving that were born before our sun had formed. They have been crossing the void for longer than our entire solar system has been alive, and they are still going. That is not a theory. That is simply what the universe does. It keeps going. It does not stop. And tonight, neither do we. Let us begin with something close, something you already know, even if you have never quite thought of it this way. The sun is a star. Your star. The one that warms your side of the planet and marks the days and makes the plants grow and fills the afternoon sky with gold. But the sun you see when you look up is not actually the sun as it is right now. It is the sun as it was 8 minutes ago. That is how long it takes light to travel the 93 million miles between the sun and your eyes. 8 minutes, which means you watch a sunset. Every time you watch a sunset, you are watching something that technically already happened. You are seeing into the past. Just slightly, just a little, but the past nonetheless. Now take that idea and stretch it. The next nearest star to our sun is called Proxima Centauri, a small red star burning quietly about 4 light years away. 4 light years, which means the light leaving it right now will not arrive here for 4 years. The light you can see from it tonight, with a clear sky and the right part of the southern hemisphere, left that star 4 years ago. You are looking at 2022 when you look at Proxima Centauri. The universe is always showing you its past. The sky at night is a kind of memory. A map of all the different moments in history, arriving at your eyes simultaneously, each star a different depth of time. This is the first gentle truth of the universe. Distance is time. When you look further out, you look further back. And the further back you look, the stranger and more beautiful things become. Our galaxy, the Milky Way, is a spiral galaxy, which means that if you could leave the planet and rise far enough above it, you would see a flat disk of stars, with arms curling outward from the centre like the pattern a spoon makes in slow cream. There are somewhere between 200 billion and 400 billion stars in this galaxy alone. That range, 200 billion to 400 billion, exists because even with all our technology, we cannot count them precisely. There are simply too many. They are too densely packed in the centre, too spread and faint at the edges. Host. We know they are there by the way their gravity moves things. We know they are there by the light they collectively produce. Counting them individually is like trying to count every grain of sand on every beach by looking at the beach from orbit. You can estimate, you can measure, but you cannot count. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. 2 trillion galaxies, each with hundreds of billions of stars. Around many of those stars, planets. Around many of those planets, moons. The numbers stop meaning anything after a certain point. They become more like the sensation of standing at the edge of the ocean and trying to hold the ocean in your mind all at once. You cannot. You are not built to, but you can stand there and feel it. And feeling it is enough. Something about that number, 2 trillion, was revised upward only in recent years. For most of the 20th century, astronomers estimated the observable universe contained perhaps 200 billion galaxies. Then a team of scientists spent years analysing deep field images, photographs taken by the Hubble Space Telescope, staring at a single tiny patch of sky, no larger than a grain of sand held at arm's length for hundreds of hours. And in that grain of sand patch of sky, they found thousands of galaxies. Thousands. In a space so small you could cover it with a thumbnail. They did the math, accounted for galaxies too faint to detect, and arrived at 2 trillion. 10 times more than anyone had thought. The universe had been hiding most of itself the whole time, and the discovery came not from building bigger telescopes, but from looking longer at the dark. The universe rewards patience. It always has. Now we move outward. Now we leave the familiar and begin to drift, because there is so much to see, and the night is long, and there is nowhere you need to be. Saturn is the planet that earns a gasp every time. Ask any astronomer who has looked at it through a telescope for the first time, and they will tell you the same thing. It does not look real. Rings are so perfectly geometric, so impossibly elegant, that the mind initially resists them. Surely that is a photograph. Surely that is a model. But it is real. It is a planet 11 times wider than Earth, wrapped in bands of pale gold and ochre, surrounded by a system of rings made almost entirely of ice and rock. Billions of pieces ranging in size from dust grains to chunks as large as houses, all orbiting the planet in a flat disk, arranged by their own gravity into bands so precise they look engineered. Rings of Saturn are not permanent. They are, in cosmic terms, relatively young, perhaps 100 million years old, perhaps 300 million, and they are slowly disappearing. The planet's gravity is pulling the ring material in, raining it down into the atmosphere at a rate of several tons per second. In 100 million years or so, the rings may be gone entirely. This means that the Saturn we see, the ringed planet, the jewel of the solar system, exists in a specific window of time. Earlier in solar system history, there may have been no rings. Later they will be gone, proused. We happen to exist at the one moment when they are present and magnificent. That is a particular kind of luck that is very hard to calculate. Saturn's largest moon, Titan. There are lakes. Not water lakes. The surface temperature on Titan is nearly 200 degrees below 0 Celsius, cold enough that water would be rock hard. But lakes of liquid methane and ethane. Dark, still, slow-moving lakes of liquid hydrocarbon. Cassini spacecraft, which spent which spent 13 years orbiting Saturn and exploring its system, photographed the northern polar region of Titan and found it dotted with these lakes, some of them as large as North American Great Lakes. The largest, called Kraken Mare, is thought to be several hundred meters deep. It rains methane on Titan. The methane evaporates, forms clouds, falls again. A hydrological cycle, the same kind of water cycle that shapes Earth's weather, but made of something entirely different. World that works the way our world works, but built from different chemistry. Cassini's last act was deliberate. In September 2017, 13 years of extraordinary science, the spacecraft ran low on fuel. Mission controllers could have left it in orbit, but an orbiting, eventually uncontrollable spacecraft posed a tiny but real risk of crashing into Titan or Enceladus, two moons that might harbour life, potentially contaminating them with Earth microbes. So they aimed Cassini at Saturn itself. They sent it in. On September 15th, 2017, the spacecraft entered the planet's atmosphere and burned up, becoming part of Saturn forever. Its final signal, faint and delayed by the distance, arrived on Earth at 7:55 in the morning. A spacecraft that had travelled billions of kilometres, survived for 20 years in the cold dark, sent back hundreds of thousands of images and decades of data, ended quietly, absorbed into the planet it had spent so long studying. The scientists in the control room wept. Of course they did. Enceladus, one of Saturn's smaller moons, only about 500 kilometers wide, which makes it smaller than the state of Texas, is one of the most scientifically exciting objects in the solar system. Beneath its smooth, icy surface, there is a liquid ocean, and from cracks near its south pole, ocean is actively venting into space. Enormous geysers of water vapour and ice particles shooting hundreds of kilometres above the surface, creating one of Saturn's rings as the material spreads and falls. Cassini flew through those geysers. It tasted them. It found water ice, organic molecules. Molecular hydrogen, which on Earth is a chemical signature associated with hydrothermal vents on the ocean floor, environments that teem with microbial life. Something warm is happening beneath the ice of Enceladus. Something is heating that ocean. In the heated dark of a buried ocean, on a moon of a ringed planet 6 times further from the sun than the Earth is. There may be life. We do not know. We have not gone back yet with the right tools, but the possibility is real. It has been written into the scientific literature with careful, precise, non-sensational language, care for a crowd, a host, and the careful precision of the language does not reduce the magnitude of the idea. There may be something living in the dark ocean, under the ice of a moon you cannot see with the naked eye from your window, and just beneath the ice of Europa, a moon of Jupiter. The same possibility waits in the same patient dark. Jupiter itself is a planet so large that all the other planets in the solar system could fit inside it. Not just could fit with room to spare. Its famous storm, the Great Red Spot, is a cyclone that has been turning continuously for at least 350 years. 350 years of uninterrupted storm. It was observed by astronomers in the 1600s with early telescopes. It was there when Newton was writing his laws of motion. It was there when the first Europeans were sailing to the Americas. It has been turning, always turning, for longer than any living person's great-great-great-great-great-grandparents have been alive. The storm is shrinking. Observations over the last century show it was once so wide that 3 Earths could fit across it, side by side. Now it is closer to 1 Earth wide, still enormous, still the most powerful storm in the solar system, but shrinking slowly by mechanisms that scientists are still working to understand. Whether it will eventually dissipate entirely or stabilize at some smaller size, no one knows with certainty. The storm keeps its own counsel. Beyond Jupiter, beyond Saturn, past the beautiful tilted world of Uranus, which rotates on its side, its poles pointing toward and away from the Sun as it orbits, making each pole experience roughly 42 years of continuous daylight, followed by 42 years of continuous night, and past the ice giant, Neptune. You reach the edge of the planetary solar system, and then the solar system continues anyway, for a long time, much longer than most people realize. The Voyager 1 spacecraft was launched in 1977. It is the most distant human-made object in existence. It has been travelling away from Earth for nearly 50 years, moving at speeds of roughly 60,000 kilometers per hour. And in that time, in those 50 years of unbroken travel, it has not even come close to leaving the solar system in any meaningful gravitational sense. It has crossed the heliopause. Now, that's the boundary where the solar wind fades and interstellar space begins. But it remains inside the gravitational reach, the Sun. The Oort cloud, a vast spherical shell of icy bodies that represents the true outer edge of our solar system, extends perhaps 1,000 times further than Voyager 1 has reached. To cross the Oort cloud entirely, at Voyager's current speed, would take approximately 30,000 years. 30,000 years at 60,000 kilometers per hour. That is the size of just our solar system. One solar system. One of 400 billion in this galaxy. There is a particular kind of silence that comes when you hold that thought for a moment. Not emptiness, silence. The way a very large space can feel quieter than a small one, even when it is full of things. The universe does not feel empty when you learn about it properly. It feels vast and full and old and still. The way the deep ocean feels when you imagine descending into it slowly. Pressure without violence, dark without absence. Life arranged in forms you had not imagined. The James Webb Space Telescope, launched on Christmas Day in 2021, and reaching its final position 1 million miles from Earth a month later, has been looking at the universe in infrared light. Wavelengths that human eyes cannot see, able to peer through dust clouds that blocked earlier telescopes entirely. Its first images, released in July 2022, showed galaxy clusters so detailed, so sharp, that scientists describe them as the deepest images of the universe ever captured. Galaxies, from when the universe was less than 1 billion years old. Young galaxies, early structures, the first light after the long dark. In the images there are arcs and rings and smears of light. Those distortions are caused by gravitational lensing, mass, where the midst of a galaxy cluster bends space itself, and the bending of space acts like a lens, magnifying the light of galaxies behind it. Einstein predicted this would happen. It does happen. You can see it in the photographs. One of the galaxies Webb observed closely is called Stephan's Quintet, a visual grouping of 5 galaxies, 4 of which are actually interacting with each other, locked in a slow gravitational dance that will eventually merge them into a single enormous galaxy. slow in human terms is misleading. The galaxies are moving at hundreds of kilometers per second relative to each other, but galaxy mergers take hundreds of millions of years to complete, which makes them appear still in any human lifetime. You could watch Stefan's quintet for 1,000 years and see no visible change. And yet it is moving. All of it is moving. The universe is never actually still. Our own galaxy, the Milky Way, is on a collision course with the Andromeda galaxy. This is not a theory or a possibility. It is a measured, confirmed trajectory. Andromeda is approaching at approximately z 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will begin to merge. The collision, and it is not quite a collision in the way you might imagine, because galaxies are mostly empty space, and the stars within them will mostly pass by each other rather than smashing together, will reshape both Krauts, galaxies entirely over hundreds of millions of years, eventually forming a single, large elliptical galaxy. Some astronomers have informally named the result Milkomeda. The Sun will likely still exist when this happens. The Earth may still exist, whether anything lives on it to watch the other galaxy fill the entire sky. That is a question the universe has not answered yet. Stars are born inside nebulae, enormous clouds of gas and dust so vast that light takes years to cross them. The process is slow at first. Region of the cloud becomes slightly denser than the surrounding gas, perhaps disturbed by the shockwave of a nearby supernova, simply by the slow accumulation of random motion, and gravity begins to draw more material toward that denser region. Slowly, tens of thousands of years, the cloud collapses. The collapsing gas heats up. Pressure builds. Core of the collapsing region grows hotter and denser, and eventually, after millions of years of slow collapse, the core reaches a temperature of about 10 million degrees Celsius, and hydrogen atoms begin to fuse into helium. Nuclear fusion ignites. A star is born. The star then spends most of its life in a balanced state. The outward pressure of fusion energy pushing against the inward pull of its own gravity, these two forces perfectly opposed, creating a stable object that burns steadily for millions or billions of years. Our Sun has been burning this way for about 4.5 billion years, and has roughly another 5 billion years of stable burning ahead of it. Compared to some stars, that is a modest life. The smallest, dimmest red dwarf stars burn so slowly, so efficiently, that they can sustain their fusion for 1 trillion years or more. The universe is currently too young for any of them to have died. Every red dwarf star that has ever formed is still burning. Massive stars live fast and die explosively. Star, 10 times. Mass of the Sun may burn for only 10 million years before it exhausts its fuel. And when it does, when the core can no longer sustain fusion, and the outward pressure suddenly fails, the outer layers of the star collapse inward, a fraction of a second, and then rebound in an explosion so violent it briefly outshines entire galaxies, a supernova. In the moments of that explosion, elements are forged that could not be made any other way. Gold, silver, uranium, platinum, the heavy elements that make up the rings on fingers and the circuits in phones and the coins in pockets. None of them existed in the original universe. They were made inside dying stars and scattered across space when those stars exploded, and they drifted through the galaxy for billions of years before gravity gathered them into new solar systems new planets, new things. You contain stardust. Not metaphorically, literally. The iron in your blood was forged in the core of a star that died before the sun existed. Calcium in your bones came from a supernova. The oxygen you are breathing right now, each atom of it was fused in a stellar core and released when that star ended its life. You are made of things that travelled across the galaxy to be here. Everything you have ever touched is made of the same ancient material. The universe is generous that way. It does not keep its best elements to itself. Black holes are the endings of the most massive stars. Objects so dense that not even light can escape their gravity. The term black hole was coined by physicist John Wheeler in 1967. The concept had existed in physics since the early 20th century. A stellar black hole forms when a massive star collapses completely, core compressed, to a point of infinite density called a singularity, surrounded by a boundary called the event horizon. The point of no return, where the escape velocity exceeds the speed of light. Nothing, once past the event horizon, comes back. Not information, not light, time in any form we understand. But black holes are not vacuum cleaners. They do not roam the galaxy sucking things in. They have gravity like any other massive object. If the Sun were replaced by a black hole of the same mass, Earth's orbit would not change at all. We would simply lose the light and warmth. The gravity would be identical. Black holes are dangerous only if you get very close, which in space, given the vast distances between things, almost nothing does by accident. At the centre of nearly every large galaxy, including our own, there is a supermassive black hole. The one at the centre of the Milky Way is called Sagittarius A star, and it has a mass of about 4 million suns. It is currently quiet, not actively consuming material in any dramatic way. But in the past it was likely far more active, and it will be again when Andromeda's galaxy merges with ours and a torrent of gas and stars falls toward the centre of the combined structure. Pulse, the sleeping giant at the heart of our galaxy, will wake. Briefly, and for tens of millions of years, the centre of what becomes Milkomeda will blaze with an active galactic nucleus. A quasar, a light so bright it will outshine the rest of the galaxy, visible across the universe. From Earth, if anything still watches from here, the centre of the galaxy will become a second sun in the sky, dimmer than our sun, but permanent, fixed, blazing through any clouds, visible even in daylight. A light at the heart of the Milky Way that burns for millions of years. The first direct photograph of a black hole was taken in 2019. The supermassive black hole at the centre of a galaxy called Messier, 55 million light-years away. The image showed a bright ring of superhired gas glowing around a central shadow. The shadow of the event horizon against the light of the Cretan disk. The image was assembled by the Event Horizon Telescope, a collaboration of radio telescopes positioned across the entire planet, from Antarctica to Hawaii to Spain, all pointed at the same target at the same time, and combined through a process of interferometry into a single virtual telescope the size of the Earth. To achieve the resolution required to image something 55 million light-years away, you need a telescope as wide as the planet. So they made one. Out of radio dishes spread across every continent, coordinated to nanosecond precision, made a telescope the size of the Earth. And they looked at the dark, and there it was. a ring of fire around an absence, exactly as physics predicted it would look. General Relativity, written by Einstein over a century ago, describing something he never imagined we would actually be able to see. And when we saw it, it looked exactly right. The universe keeps confirming the math. It keeps matching the predictions. And every time it does, the scientists who spent their careers on those predictions feel something that is very close to what a musician feels when a piece they have been writing for years finally comes together in performance. Recognition, arrival. We have been sending radio signals into space since the early 20th century. The first broadcasts, radio, then television, then radar, have been moving outward from Earth at the speed of light for about 100 years, which means there is a human radio noise spreading through the galaxies sent on us our sun, currently about 200 light years wide. Within that sphere, any civilization with sufficiently sensitive instruments could potentially detect that something here is transmitting 200 light years. That sounds large until you consider that the Milky Way galaxy is about 100,000 light years across. Our radio bubble occupies about 1/10,000th of the diameter of just our galaxy. We have barely whispered into an ocean. A question of whether anyone is listening has not been answered. The SETI program, the Search for Extraterrestrial Intelligence, has been scanning the sky for signals since the 1960s. For listening across many frequencies for anything that does not match natural patterns. There have been anomalies over the years. The most famous, the WOW signal, detected in 1977 at the Big Ear radio telescope in Ohio. A signal so strong and so narrow in frequency that the astronomer monitoring the printout circled it and wrote the word WOW in the margin. It has never been detected again. It has never been explained to universal scientific satisfaction. It remains in the literature as unresolved. Something narrowband coming from the direction of the constellation Sagittarius, arriving once and never returning. The radio telescope that detected it no longer exists. It was demolished in 1998 to make way for a golf course. The universe has a sense of irony, or perhaps it simply does not care about our timetables. Somewhere past the outer edge of what we can see, past the observable universe, which is bounded not by physical walls, but by the distance light has had time to travel since the Big Bang. The universe continues. We do not know how far. We do not know if it is infinite or simply very large. We know only that what we can observe is itself so immense that all 2 trillion galaxies and all the hundreds of billions of stars in each of them fit within a sphere about 93 billion light years wide. 93 billion light years in every direction. And beyond that boundary, the universe simply continues in ways our light has not yet reached us to describe. There is a specific kind of wonder that comes when you think about the cosmic microwave background radiation. The faint afterglow of the Big Bang itself still present everywhere in the universe. A whisper of warmth spread uniformly in every direction, detectable by radio telescopes as a uniform hiss. It was discovered accidentally in 1965 by 2 Bell Labs engineers, Arno Penzias and Robert Wilson, were trying to use a large radio antenna for satellite communications and kept detecting an inexplicable noise that seemed to come from everywhere equally. They checked their equipment. They removed a pair of pigeons that had nested in the antenna and cleaned up what they politely called white dielectric material. The noise remained. It was coming from the entire sky, simultaneously, uniformly, in every direction. They eventually contacted a team of physicists at Princeton who had been theorizing about just this kind of signal and had been preparing to look for it. And the Bell Labs engineers had already found it, by accident, while trying to get rid of a pigeon problem. The signal they had been fighting was the echo of creation. The oldest light in the universe, redshifted by billions of years of expansion into the microwave range, arriving at their antenna from 13.8 billion years ago. You could build a radio receiver that could hear the signal tonight. It is still there. It will always be there. The universe broadcasting itself quietly to everything that has ears tuned to the right frequency. The stars tonight are doing the same thing. Each one transmitting, each one patient. Each one carrying some portion of the universe's long memory in the light it sends out across the dark. Dark between them is not empty. It never was. Between the galaxies, between the stars, between the atoms of every piece of matter in the universe, space is laced with something physicists call dark matter. Invisible, undetected directly, but evidenced by the way galaxies rotate and cluster and bend light in ways that visible matter alone cannot explain. There is approximately 5 times more dark matter in the universe than ordinary matter. 5 times more of something we cannot see, cannot touch, cannot identify, than everything we have ever observed, photographed, named, or studied. The universe is mostly made of things we do not understand yet. And beyond dark matter, woven into the structure of space itself, there is dark energy. The force that is causing the expansion of the universe to accelerate. When the Big Bang occurred, everything moved outward. Intuition suggests this expansion should be slowing, the way a ball thrown upward slows as gravity pulls it back. Instead, measurements taken in the late 1990s showed that the expansion is speeding up. Galaxies are moving away from each other faster over time, not slower. Something is pushing space itself apart. We call it dark energy. We do not know what it is. We know it makes up roughly 68% of the total energy content of the universe. We know its effect precisely. We do not know its nature at all. The universe has been generous with its mysteries. It gives us more than we solve. Fust. Every answered question opens 3 new ones, deeper and stranger, pulling curiosity forward the way a story pulls a reader forward. Not with the promise of ending, but with the pleasure of continuing. The Hubble Space Telescope looked at a tiny patch of seemingly empty sky for over 11 days. In 1995, a region of the sky containing, as far as anyone could tell, nothing. No bright stars, no known galaxies, just dark. And in that dark, after 11 days of exposure, an image resolved that became known as the Hubble Deep Field. Nearly 3,000 galaxies in a patch of sky you cover with the eraser of a pencil held at arm's length. Nearly 3,000 galaxies, each one containing hundreds of billions of stars, a piece of sky that looked like nothing at all. The universe does not announce itself. You have to look at it quietly for a long time before it shows you what it holds. And it holds so much. It always has. It held this planet long before the planet held anything alive. And it will hold whatever comes after us with the same patient indifference it holds everything. Not coldly, not cruelly, but the way a very old and very large thing holds all the smaller things that happen within it. The way a forest holds the sound of something moving through the trees at night, and the movement matters. And the sound is real, even if the forest itself does not notice. The stars above you right now, the ones visible through whatever window or beneath whatever sky you carry, in your mind as you listen, are not decorations. They are not backdrop. They are places. Each one is a sun with the same right to that name as ours, burning with the same nuclear fire, older or younger or smaller or larger, but fundamentally the same. Fusion at the core, light at the surface, warmth, and travelling outward in all directions across the years and decades and centuries it takes to arrive anywhere at all. Some of that light is arriving here tonight. On your side of the planet, on the dark half, on the hemisphere turned away from our local star and exposed to all the others. The light is falling on everything, on the fields and the oceans and the mountains and the cities with their own competing light. On you. You are not outside the universe, looking at it. You are inside it. Built from it. Every atom in you has been part of this story since near the beginning, forged in a star, scattered in an explosion, gathered by gravity, assembled by chemistry, into something that can lie in the dark. And think about the stars it came from. The universe in you, looking at itself, finding it beautiful. The story is not finished, not even close. There are 2 trillion galaxies, and we have visited exactly none of them, and barely studied any of them. And each one contains wonders that no human being has ever imagined, and no instrument has ever pointed at. The universe has been making them patiently for nearly 14 billion years, without asking whether anyone would ever come to look. Tonight we have made a start. We have drifted out past the planets, and past the edge of the solar system and past the nearest stars, and looked back at the galaxy from outside and turned around to face the dark. The beautiful, enormous, patient dark, full of galaxies and signals and ancient light and questions no one has yet thought to ask. The journey is just beginning. Also, there are oceans beneath the ice of moons we have only photographed from orbit. And in those oceans, the dark and pressured and chemically alive in ways we have not measured yet, and something may be moving in it, patient and ancient, and entirely unaware that somewhere far above the ice, across 600 million miles of space, small blue planet spent 100 years pointing its best instruments at the sky, and wondering if anyone else was out there. The ice of Europa is 40 kilometers thick in some places, and beneath it, an ocean that has been dark for longer than human civilization has existed, waits in a silence so complete. It makes the silence of space seem loud by comparison. Jupiter's gravity needs that moon-like dough, the same tidal flexing that keeps Io volcanically violent, keeps Europa's ocean liquid, keeps it warm enough to remain water instead of becoming the frozen shell the surface suggests. From space, Europa looks like a cracked egg, its surface laced with rust-coloured lines where the ice has fractured and refrozen over millions of years. Those lines are a record of movement, tide, of a moon that has been slowly shifting and groaning under Jupiter's pull for billions of years. They are, in a sense, the most ancient writing in the solar system. Not meaning anything, but marking something, the passage of enormous time, persistence of water in the dark. The ocean beneath that, ice, maybe be twice the volume of all of Earth's oceans combined. All our seas, the Atlantic, the Pacific, the Arctic, every lake and river and aquifer, and then double it. Held inside a moon smaller than our own, place no sunlight has ever reached. Under ice you could not melt with the most powerful machines humanity has ever built. If life exists there, it has never seen light. It has evolved, if it has evolved at all, in total chemical darkness, drawing energy from hydrothermal vents or chemical gradients, the way the strangest and most ancient organisms on Earth still do at the bottom of our own oceans. The tube worms and vent crabs and microbial mats around hydrothermal systems on Earth's ocean floor live entirely without sunlight. They eat heat. They eat chemistry. They were here before the surface of the planet had complex life, and they persist in their own deep world, patient and completely indifferent to everything happening above them. If something lives under Europa's ice, it is probably something like that. Probably small, probably ancient, probably uninterested in the concept of the universe above it in any way we could recognize as interest. But alive in the dark, metabolizing, replicating, filling whatever niche chemistry and warmth have carved out for it in that deep and lightless sea. The Europa Clipper spacecraft, launched in October 2024, is currently travelling toward Jupiter. It will arrive in 2030 and begin making dozens of flybys of Europa, studying the ice, the ocean, the chemistry of the plumes that may vent from the surface, the way Enceladus vents into space. It carries instruments that can detect biosignatures, chemical signs of life in any material it samples. It will not land, it will not drill, but it will listen, in its own instrument language, to everything the moon is willing to say from outside. We sent a spacecraft to ask a moon if anything lives inside it. That is the kind of thing the human species does now. That is what all the mathematics and the physics and the engineering was building toward. The ability to ask the universe, quietly and precisely, whether we are alone. The question has not been answered yet, but it is being asked. Right now, as you are here, and the night is here, and the stars are turning overhead, a spacecraft is crossing the solar system toward a moon with an ocean in it, but the ocean does not know it is coming. Jupiter has 95 confirmed moons, 95, each one different. Some are small and dark, and captured asteroids, rubble that wandered too close and was caught by Jupiter's immense gravity, and has been orbiting since. Irregular, battered, carrying in their composition the record of the early solar system's violence and chemistry. Others are large and complex. Ganymede, the largest moon in the solar system, larger than the planet Mercury, has its own magnetic field, phenomenon so unusual for a moon that when it was confirmed, it required a revision of the models scientists used to understand what kinds of objects could generate magnetic fields and why. Something in Ganymede's interior is still moving, still convecting, still generating the electric currents that produce magnetism. A moon the size of a planet, quietly doing things moons were not supposed to do. Io, the innermost of Jupiter's large moons, is the most. volcanically active body in the solar system. Its surface is covered in sulfur compounds in shades of yellow and orange and white, resurfaced constantly by eruptions from hundreds of active volcanoes. The tidal forces from Jupiter are so powerful that they flex Io's interior continuously, generating enough heat to keep vast regions of its interior molten. Some of Io's volcanic plumes reach hundreds of kilometers above its surface. The entire moon smells, if smell were possible in its thin sulfur dioxide atmosphere, like the inside of a struck match. It is a world that cannot rest, that has never rested, that has been erupting continuously since it formed, and will continue erupting as long as Jupiter's gravity holds it in its current orbit. Stand far enough back, and the Jupiter system begins to look less like a planet with moons and more like a miniature solar system, a central massive body surrounded by a diverse collection of smaller worlds, each with its own character, each shaped by its particular relationship with the gravity at the centre, the same gravitational physics that organises planets around a star, organises moons around a gas giant. The universe uses the same patterns at different scales. It is efficient that way. It finds a solution and applies it everywhere. This self-similarity, the same patterns appearing at vastly different scales, runs through the universe like a theme in music. The spiral of a galaxy mirrors the spiral of a hurricane, which mirrors the spiral of a nautilus shell, which mirrors the structure of certain proteins. Not because the universe is making a poetic statement, but because the mathematics of how rotating systems organize themselves under the influence of gravity and angular momentum produces similar shapes regardless of scale. The universe does not know it is being beautiful. It is simply following its own rules, and the rules turn out to produce spirals wherever you look. Beyond Jupiter and Saturn, in the outer solar system, where sunlight is so dim it arrives, like starlight, rather than warmth, the ice giants, Uranus and Neptune, wait in their blue-green cold. Both are classified as ice giants because they contain large amounts of water, ammonia and methane, in a slushy, pressurized state that is neither quite liquid nor quite solid. A phase of matter, sometimes called a superionic phase, where the oxygen atoms form a crystal lattice, while the hydrogen atoms move freely through it, like a liquid conductor, deep in the interiors of Uranus and Neptune, under pressures millions of times greater than Earth's atmospheric pressure. It may rain diamonds. The carbon in the methane atmosphere gets compressed under extreme pressure and heat until it crystallizes, and those crystals, diamonds, real diamonds, may fall through the fluid interior, sinking toward the core, accumulating in vast quantities that no human technology will ever reach. Neptune has diamonds falling inside it right now. Not in the future, not theoretically. Right now, as you are here, as the dark outside your window is full of its usual sounds, blue planet 6 times farther from the sun than Jupiter is slowly raining diamonds into its own core. The universe is doing this without any ceremony, without any announcement. It has been doing it since Neptune formed, and it will keep doing it, and it requires no audience and no acknowledgement. But you know about it now. You are one of the few things in this solar system that does. Neptune was discovered through mathematics before it was ever seen through a telescope cloud. In the mid-19th century, astronomers noticed that Uranus was not quite where calculations said it should be. Its orbit had small irregularities, tiny deviations from the path Newton's laws predicted. Rather than concluding that Newton's laws were wrong, two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently concluded that something must be perturbing Uranus from outside. Another planet, large and unseen, pulling on it gravitationally. They each calculated where that unseen planet should be. Le Verrier sent his calculations to the Berlin Observatory, and on the night of September 23rd, 1846, the astronomer Johann Galle pointed a telescope at the position. Le Verrier had calculated and found Neptune within 1 degree of where the mathematics said it would be. A fact found by pure thought. By someone sitting at a desk with pencil and paper, reasoning from the wobble of another planet's path, calculating where something invisible must be. The universe confirmed it the first night anyone looked. This is what physics does at its best. It tells you where to look. And when you look, the thing is there. The same process, applied to Mercury's orbit in the late 19th century, produced a prediction of a planet inside Mercury's orbit. A planet called Vulcan, which would explain the precession of Mercury's perihelion. Astronomers looked. They found nothing. For decades the anomaly remained unexplained. A small irritation in otherwise perfect theory until Einstein's general relativity appeared in 1915 and explained the precession without any new planet at all. The curvature of space-time near the Sun was distorting Mercury's orbit in exactly the way general relativity predicted. The math was not wrong. The model had just been incomplete. And when a more complete model arrived, it explained everything without adding anything new. General relativity is still the most precisely confirmed theory in the history of science. Every test ever devised to challenge it has confirmed it. Bending of light around the Sun, observed during a solar eclipse in 1919. Gravitational time dilation, confirmed by comparing atomic clocks at different altitudes. A clock on a mountain runs very slightly faster than a clock in a valley, because gravity is slightly weaker at altitude. Gravitational waves, ripples in the fabric of space-time itself produced when massive objects accelerate, detected for the first time in September 2015 by the LIGO Observatory. That first detection was caused by two black holes, each roughly 30 times the mass of the Sun, spiraling toward each other, and merging about 1.3 billion years ago. The collision released more energy in a fraction of a second than all the stars in the observable universe combined emit in that same fraction of a second. The ripple from that event, after travelling 1.3 billion light-years, distorted the LIGO detector by less than 1,000th the width of a proton. 1,000th the width of a proton, smaller than any scale we have direct experience of, measured, confirmed, real. The scientists who built LIGO spent 40 years and over $1 billion building an instrument sensitive enough to detect that distortion. They aligned mirrors kilometers apart to a precision finer than the width of an atomic nucleus. They isolated the instrument from every conceivable vibration, traffic, wind, the footsteps of the technicians, microseismic hum the ocean makes as waves press on the seafloor. They reduced the noise floor of the instrument until the quantum behavior of light itself became the dominant source of uncertainty. And Then they found ways to push below even that, using a quantum technique called squeeze to reduce the photon noise in the laser beam. They built the most sensitive measurement instrument in human history, and they pointed it at empty space, and they waited, and the universe obliged when the first signal arrived. A chirp, a sweep of frequency lasting a fraction of a second, a sound the detector's votes converted into audio that journalists around the world played on repeat the day of the announcement. It was a sound that had never been heard before. Not because no one had listened, because the universe had not produced a signal quite like that within detectional range since the detectors were running. The merger of those two particular black holes in that particular place, producing that particular wave, arriving at that particular moment. A sequence of cause and effect, stretching back 1.3 billion years, concluding in a fraction of a second of rippled space-time, recorded in a Louisiana and Washington state simultaneously confirmed as real. The universe had been keeping that appointment for over 1 billion years. Gravitational wave astronomy has since become its own field. Dozens of detections now. Black hole mergers. Neutron star mergers. And in those neutron star mergers, something extraordinary. When two neutron stars spiral together and collide, the collision creates a kilonova. An explosion so energetic that it briefly synthesizes heavy elements in enormous quantities. Gold, platinum, uranium. The collision of two neutron stars in August 2017, detected both in gravitational waves and in light across the electromagnetic spectrum, observed to have produced gold in an amount roughly 100 times the mass of the Earth. One collision, one event, gold enough to make every piece of jewellery ever crafted in human history, and then an incalculable amount more scattered across space to drift through the galaxy until gravity somewhere gathers it up again. The gold in your rings, if you have them, gold in every vault and every circuit and every trophy and every coin, it came from events like that one. Ancient collisions in the dark, long before the solar system existed, scattering wealth across the galaxy for gravity to collect. The stars are generous. They do not hoard what they make. Between the stars, space is not truly empty. The interstellar medium, the gas and dust that fills the galaxy between the stellar systems, is extraordinarily thin by any standard you might apply. In some regions, a cubic centimetre of space contains only a single atom per cubic centimetre. Best vacuum humans have ever produced in a laboratory still contains thousands of molecules per cubic centimetre. Space between stars is emptier than anything we can make, and yet it is not nothing. Across the vast distances between stars, thinness accumulates into something meaningful. The molecular clouds where stars form are made of this material. Hydrogen, helium, traces of carbon and oxygen and nitrogen, and more complex molecules that build up over millions of years on the surfaces of dust grains and on through a slow chemistry that resembles in some of its products the building blocks of life. Amino acids have been found in meteorites, molecules from which proteins are assembled. The molecular alphabet of biology form in the interstellar medium and in the clouds around, forming stars incorporated into the dust and ice of protoplanetary disks, falling with the material that builds planets. They were here before the Earth finished forming. They were raining down on the young planet along with everything else, crowd. Hamas, whether the amino acids in meteorites contributed directly to the origin of life on Earth is still debated, but the fact that they form naturally in space, partially space, without biological processes, in the cold chemistry of the interstellar medium, suggests that the molecules of life are not rare. They are what the universe makes when it has the right elements and enough time. The universe has been making the ingredients of life for nearly 14 billion years, spreading them through every solar system, every nebula, every collision and outflow and stellar wind. If life requires certain molecules, those molecules are everywhere. If life requires liquid water exists beneath the ice of moons, around gas giants, and almost certainly around many of the billions of planets we have not yet observed. If life requires energy gradients, differences in temperature or chemistry that drive metabolic reactions, the universe provides energy gradients in abundance wherever geology and chemistry operate. The conditions for life are not rare. What we do not yet know is whether the spark, the moment when chemistry becomes biology, when molecules begin to replicate and metabolize and evolve, is common or vanishingly rare. That threshold may be crossed easily wherever the conditions are right. Or it may have happened once, by chance so improbable it will never happen again in this universe. We genuinely do not know. We have exactly one confirmed example of life, and one example is not enough to calculate a rate. The universe is very large. Even a vanishingly small probability, multiplied by the number of places where conditions are right, may still produce an enormous number of outcomes. The math of rarity and scale works in strange ways when the scale is 2 trillion galaxies. There are stars in this galaxy that are 12 billion years old. Stars that were burning when the universe was less than 2 billion years old, when the cosmos was still dense and young, and galaxies were still dense and young, galaxies colliding and merging into their current forms, when the heavy elements we take for granted were still rare and being manufactured for the first time in the cores of massive stars and spread for the first time through the first supernovae. Planets may have formed around some of those ancient stars. Life may have had 12 billion years to develop, whatever it became in that time. If it became anything at all, it has had a head start on us of billion years. 8 billion years is long enough that the concept of technology becomes meaningless as a comparator. Whatever of a civilization becomes in 8 billion years is as far beyond our imagining as our current civilization is beyond the imagining of the first single-celled organisms that appeared in Earth's oceans. The comparison does not fail for lack of intelligence on our part. It fails because the timescale is simply outside the range of useful analogy. There is a moment, somewhere in all of this, where the science stops being a collection of facts and becomes something more like a feeling, where the numbers, distances, the distance, and the timescales accumulate until they exceed the mind's capacity to hold them individually, and instead they settle into something ambient, a sense of scale, of depth, of being, inside something almost incomprehensibly vast and old and intricate. Something that has been making suns and scattering diamonds and writing gravitational waves and building the molecules of life for so long that what we call history is barely a breath. It is not a frightening feeling, this sense of scale, or it does not have to be, can be the opposite it. A kind of release. The discovery that you are small is also the discovery that most of the burden is not yours. The universe was here before any problem you are carrying. It will be here long after. Your particular worries, as real as they are, occupy a very specific and very temporary corner of something that has no corners. The darkness that holds you tonight holds everything else too, without effort, without tiring, without any consciousness of the holding. The light from a star called Deneb, in the constellation Cygnus, takes roughly 2,000 years to reach us, which means the Deneb you can see on a clear night is the Deneb of 2,000 years ago, a star burning at a time when the Roman Empire was still whole, when no one on this planet had the slightest idea what a star actually was. The night sky was simply beautiful without being understood. The light left then, and has been travelling since, crossing the distance year by year, and now it arrives at this planet, and some of it falls on a window, and comes through to wherever you are. 2,000 years of travel. Arriving now, quietly, without announcement, in the dark. There is so much still ahead of us in this journey. Deeper into the galaxy's spiral arms, to the violent and beautiful regions where stars are forming right now in clouds of gas and dust, toward the outer reaches where the oldest stars burn in the galaxy's halo, toward the first galaxies that formed. When the universe was young and dense and utterly unlike the place it has become, pulsars defined. Collapsed stars spinning hundreds of times per second, sweeping beams of radio waves across the galaxy, like impossibly precise cosmic lighthouses. There are magnetars. Magnetic fields are so powerful that the energy they store would be lethal to a human. Standing the distance of the moon away, there is the cosmic web. There is the cosmosphere, the largest structure in the universe, a filamentary network of dark matter along which galaxies cluster like dew on a spider web, stretching across hundreds of millions of light years. A structure so large that the Milky Way is less than a mote of dust within it, all of it waiting in the dark beyond the edge of what tonight has shown you. All of it patient, all of it real. The universe has been keeping these places exactly as they are, unchanged and waiting, for the entire span of human existence. They were there before you were born. They are there now. They will be there when you wake tomorrow, exactly as described, exactly as vast, the same ancient light still moving through the same ancient dark, the same patient storms turning on the same distant worlds, the same oceans pressing against the same ice from below, waiting for a knock that has not yet come. There is a place in the universe where two stars orbit each other so closely that they complete a full revolution in less than a day. Not a year, not a month, a day. They are called contact binaries, and in some cases the stars are so near that their outer atmospheres touch and material flows between them. Like water between two connected pools, each star drawing from the other, sharing mass, sharing heat, locked, a host, locked in an embrace that will last millions of years before one of them grows too large, and the system destabilizes and ends in something neither star could have avoided from the beginning. The universe makes these pairings and keeps them. Two suns sharing their fire in the dark, turning around each other in the time it takes the Earth to rotate once. Most stars in the galaxy are not alone. Most of them have companions, binary systems, triple systems, quadruple systems, stars in gravitational relationships that can last billions of years, each one influencing the other's evolution in ways a solitary star never experiences. Our Sun is unusual in its solitude. It travels through the galaxy alone, which may be one of the reasons the inner solar system is stable enough to have held a rocky planet in a liquid water orbit for 4.5 billion years. A companion star would have perturbed things, would have introduced gravitational chaos into the delicate orbital architecture that keeps Earth where it is. The Sun's loneliness, if you want to call it that, may be one of the preconditions for everything that came after it. There is something in that worth sitting with for a moment. Not sadness, just the recognition that certain kinds of flourishing require a particular kind of space around them, that the conditions for something extraordinary to grow are sometimes quieter than you might expect. The galaxy itself moves, not just the stars within it. The galaxy as a whole, along with its 2 trillion neighbours, participating in large-scale flows that cosmologists have been mapping for decades. There is a region toward which our galaxy, and many of the galaxies around us, appear to be gravitationally drawn, a vast concentration of mass called the Great Attractor, located roughly 250 million light-years away, in the direction of the constellation Centaurus. Milky Way is moving toward it at roughly 600 kilometers per second. The local group of galaxies, the Milky Way, Andromeda, Triangulum Galaxy, and several dozen smaller companions, all moving together in the same direction, drawn by something massive enough to be felt across hundreds of millions of light years. For a long time, the Great Attractor was hidden from direct observation by the plane of the Milky Way itself. The dense disk of stars and dust through which we look when we face that direction blocks visible light almost completely. Astronomers had to use X-ray and radio observations to see through the disk. What they found was a supercluster of galaxies. Thousands of galaxies concentrated in a region of space so rich with mass that its gravitational influence extends far beyond what any individual galaxy could produce. We are falling toward it, slowly by human timescales, inexorably by any honest accounting. The fall will take far longer than the current age of the universe to meaningfully close the distance. We are in freefall, and we do not feel it. The Earth falls around the Sun without feeling the fall. The Sun falls around the galactic centre without sensing the motion. The galaxy falls toward the Great Attractor without any internal awareness of pull. Everything in the universe is falling towards something else, and from the inside the falling feels like stillness. This is what orbits are. They are falls that keep missing. The Earth falls toward the Sun constantly moves sideways fast enough that it keeps missing, curving around and around in a path that never closes the distance. Take away the sideways motion and it falls in. Add more sideways motion and it spirals out. Precise balance of falling and moving sideways that produces a stable orbit is, in a universe this large and active, actually quite common. Gravity and angular momentum are patient collaborators, but the elegance of it, seen clearly, never quite loses its ability to cause a small internal stillness. The planet you are on is missing the Sun every moment, has been missing it for 4.5 billion years. will keep missing it for 5 billion more. The moon is doing the same thing. Right now, while the night hold, whatever part of the world you are in, the moon is falling toward the Earth and missing it. In the dark, above whatever clouds cover you, moving through its orbit at roughly 1 kilometer per second, close enough that its gravity pulls the oceans into tides, far enough that its light, when the sun illuminates it, takes just over a second to reach you. 1 second. The moon is a light second away. Everything else in the universe is so much further that the moon, in terms of light travel time, might as well be in the same room. Apollo astronauts spoke about the journey to the moon in ways that were not always captured by the official transcripts. The private recordings, the later interviews, reveal something that the mission parameters did not prepare them for. The overwhelming visual reality of looking back at the Earth from a distance. Not the overview effect exactly, though that was part of it. Something quieter, the realization that the line between night and day on the surface of the Earth, the terminator, visible from lunar distance as a soft curve of shadow creeping across the planet, was moving. You could watch it move if you watched long enough. The planet was rotating, visibly, slowly, the shadow line advancing, and behind it the side of the Earth moving into darkness, and ahead of it, the side moving into light, and all of it happening with the silence and the patience of something that has been doing this for billions of years and requires no acknowledgement. Edgar Mitchell, who walked on the moon during Apollo 14, described looking out the window of the command module during the return journey and experiencing what he later called a flash of understanding, a sudden, wordless recognition that the universe was in some sense conscious, or at least that his separation from it was an illusion, that the atoms of his body and the atoms of the stars were not different kinds of thing, but the same kind of thing arranged temporarily into different configurations. He was a scientist and an engineer, and he was careful about how he described this. He did not claim mysticism, he claimed perception. The sense that something was true that the instruments could not measure. Whether he was right in any formal sense is a question for a different kind of inquiry, but the feeling he described is one that the science itself keeps approaching from the outside. Side, without ever quite naming it. The fact that we are made of stellar material. The fact that consciousness is the universe examining itself. The fact that the same forces that shape galaxies shape the neurons that think about galaxies. There is something in all of that which is not fully contained by any equation, not fully expressed by any measurement, not quite finished when the data is collected and the papers are written. It is the part that remains after the science has said what it can say. It lives in the space between the facts, in quality of attention that the facts, properly understood, seem to require. The Crab Nebula is what is left of a star that exploded in the year 1054. Chinese astronomers recorded the event. A star so bright it was visible during the day for 3 weeks, and at night for almost 2 years, called it a guest star. In the centre of the expanding cloud of gas and dust it left behind, there is a pulsar, the collapsed remnant of the star's core, now a sphere of neutrons about 20 kilometres across, spinning 30 times per second, so dense that a teaspoon of its material would weigh as much as a mountain. It sweeps a beam of radiation around the galaxy 30 times, every second, regular as a clock, more accurate than most clocks humans have ever built. Crab pulsar drifts less than 1 second per 300 years. It is a clock made by an explosion, running on the angular momentum of a collapsed star, keeping time in a nebula full of its own remnant light. Pulsars were discovered in 1967 by a graduate student named Jocelyn Bell Burnell, who was monitoring radio telescope data and noticed an anomalous signal. Regular pulsars arriving every 1.33 seconds, so regular and so precise that the astronomers initially, briefly, jokingly labelled the source LGM-1. Little green men, not because they believed it, because nothing natural was supposed to pulse that precisely. Nature was supposed to be messier than that, when the natural explanation, a spinning neutron star sweeping its beam across the Earth with every rotation, was understood, was not disappointing. It was more astonishing than the joke had been. The universe had made something more accurate than a clock out of the remains of a dead star by accident, and it had been ticking in the dark for millions of years before anyone pointed a radio dish at it, heard the beat. Bell Burnell did not share in the Nobel Prize awarded for the discovery of pulsars. Her supervisor and his colleague received it instead. She has spoken about this with remarkable grace over the years. Not bitterness, not only bitterness, but a kind of long view that seems appropriate for someone who spent her career studying objects that put human timescales in place. The universe does not keep score. It just keeps making things worth finding. There are more than 3,000 known pulsars in the Milky Way, and the galaxy is estimated to contain at least 100 million neutron stars in total. The dead cores of stars that were not quite massive enough to collapse into black holes, sitting in the dark throughout the galaxy, cold and dense and quiet, no longer fusing anything, no longer radiating significantly, just there. Patient remnants, stellar graves, scattered through the arms of the galaxy, in numbers too large to count individually. Some of them may have planets still orbiting them. The wreckage of solar systems that survived the supernova, or new planets that formed from the debris disk that sometimes assembles around a neutron star after the explosion. First confirmed exoplanets ever discovered were around a pulsar, not around a sun-like star. Around a dead star, spinning 30 times a second in the remnants of its own explosion, with rocky planets orbiting it in the dark, without warmth, bathed in radiation. The universe finds ways to arrange planets around things. It has a tendency toward that particular shape, a central mass, smaller bodies circling it, because that is what angular momentum and gravity produce when given time and material. Everywhere you look that the conditions are right, you find the same pattern. Moons around planets, planets around stars, stars around galactic centres, galaxies drawn toward attractors. The same falling and missing over and over at every scale, the universe endlessly repeating its favourite arrangement. Among the stars forming right now, and stars are forming right now, in the nebulae that the James Webb Space Telescope has been imaging in extraordinary detail, there are stars that will outlive the current age of the universe many times over. The smallest red dwarfs, cool and dim, burning hydrogens so slowly and so efficiently that their lifespan extends to trillions of years. There are stars in the galaxy that have been burning since within 1 billion years of the Big Bang, and they will still be burning when the universe is 1,000 times its current age. They have seen everything that has happened in this galaxy since almost the beginning. Every star that has formed and died, every supernova, every planet that has assembled and been destroyed. The rise and, presumably, fall of any civilizations that has ever existed in the galaxy. They have continued burning through all of it. Too cool and quiet to be dramatic, too efficient to exhaust themselves. Patient beyond any timescale that means anything to anything that lives. And dies in the normal range of years. 5 billion years. When our sun begins to expand into a red giant, swelling outward, its outer layers expanding beyond the orbit of Venus and perhaps beyond the orbit of Earth, the inner solar system consumed in slow fire. Those red dwarf stars will be entering what is, for them, early middle age. They will barely have noticed the time. The red giant phase of the sun is not the end of the sun. It is a transition. The outer layers, expanding and cooling, will form a beautiful structure called a planetary nebula. A shell of glowing gas pushed outward by the stellar wind, lit from inside by the now exposed core. From a distance it will look like a flower of light. The inner planets, whatever remains of them, will be absorbed. The outer planets, Jupiter, Saturn, Uranus, Neptune, may survive in altered orbits, and at the centre, the Sun's core will remain as a white dwarf. A sphere about the size of the Earth, made of carbon and oxygen, no longer fusing anything, cooling slowly over billions of years, radiating the last of its stored heat into space. White dwarfs cool very slowly. Calculations suggest that to cool from a white dwarf to a black dwarf, a completely cold, dark, inert stellar remnant, takes longer than the current age of the universe. Much longer. The universe is not old enough yet for any white dwarf to have fully cooled. Every white dwarf that has ever formed is still warm, still glowing faintly in the dark, still releasing the last of the energy it stored when it was a living star, slower and quieter, with each passing billion years, but not yet finished. The sun will become one of these, eventually. A dim white coal in the dark, surrounded by the cooled and silent remnants of its planets, cooling on a timescale that makes all of human history into something too brief to measure. And even then, even in that final quiet, there will be something left. Something that was here, burned for 9 billion years, and made light that warmed this planet and allowed everything on it to exist. There is a class of object called a magnetar that represents perhaps the most extreme stable matter in the universe. A neutron star with a magnetic field so powerful it is almost impossible to describe in terms that connect to anything in ordinary experience. Magnetic field of a magnetar is roughly 1,000,000,000 times stronger than Earth's magnetic field. At a distance of 1,000 kilometers, the field would be strong enough to distort the electron clouds of atoms in your body, changing the chemistry of your cells. At closer range, would be fatal, many times over in ways that have no analogy in human experience. And yet, these objects sit in the galaxy, stable, turning slowly, their fields gradually weakening over thousands of years, until they become ordinary neutron stars. They are not aggressive. They do not move toward things. They simply exist with an intensity that the universe permits at the extremes of what matter can become. December 2004, a magnetar roughly 50,000 light-years away in the constellation Sagittarius released a burst of energy in a fraction of a second that was the most powerful event ever recorded from outside the solar system. The burst lasted about a tenth of a second. In that tenth of a second, it released more energy than the sun emits in 100,000 years. The wave of gamma rays and X-rays arrived at Earth and measurably ionized the upper atmosphere. Not enough to cause harm, not even enough for most instruments to notice, but measurably, detectably, faint impression made on this planet from 50,000 light-years away. Ghost of an explosion reaching across half the galaxy to leave a mark no larger than a whisper on the edge of the sky. Host. The universe has these moments of intensity written through it and separated by the long, quiet stretches that make up most of its history. The explosions and the mergers and the magnetar flares are not the normal state of things. The normal state of things is exactly this: a long, patient turning, stars burning at their steady rate, planets moving in their orbits, galaxies drifting slowly along their paths toward each other and away. The cosmic microwave background cooling by fractions of a degree over billions years. The universe expanding steadily at the rate dark energy permits. Everything moving in a direction and at a pace that contains no urgency, deadline, no hurry at all. As you are breathing right now, the universe is expanding. Every cluster of galaxies moving away from every other, the space between them stretching, the universe becoming slightly larger with every passing second. Not because things are flying apart from a centre, but because space itself is growing in every direction simultaneously. The way the surface of a balloon grows when you inflate it, not from any particular point, but everywhere at once. There is no centre of the expansion. Every point in the universe is equally the centre of the expansion. From anywhere you stand, everything else is moving away from you. It is the most democratic thing the universe does. It expands equally for everyone. The most distant objects observable are not in a particular direction. They are in every direction equally. The edge of the observable universe. The sphere of space from within which light has had time to reach us surrounds us completely in every direction, a perfect shell. With us at the centre, not because we are special, but because observation always places the observer at the centre of what can be seen. From Andromeda, the observable universe is centred on Andromeda. From a galaxy at the farthest edge of our own observable sphere, the universe extends in all directions around them, most of it in directions we will never see. This is the thing that is hardest to hold and also the most beautiful once you let yourself try. There is no outside to the universe. There is no edge with something beyond it. There is only inside. Everything that exists is inside the same thing, participating in the same expansion, subject to the same physics, made of the same handful of fundamental particles arranged in patterns of increasing complexity, from hydrogen atoms to stars to galaxies to the filaments of the cosmic web, to whatever comes after that, if anything does, somewhere in the middle of all of this. Not at the centre of anything, not at a significant position in any cosmological sense. A small rocky planet orbits an ordinary yellow star in the outer arm of a spiral galaxy, carrying on its surface a thin film of life that has, in the last few thousand years, figured out enough of the rules of the universe to look back at it with some understanding. To measure the expansion, to detect the gravitational waves, to photograph the black holes, to find the amino acids in the meteorites and recognize them, to lie in the dark and think about all of it. That is not an accident the universe arranged. But it is not random either. It is what happens when the right chemistry has enough time. It is what matter does when the conditions allow it to become complex enough, to become curious. And curiosity, once started, does not stop easily. There are light echoes in astronomy, a phenomenon where a burst of light from a stellar explosion spreads outward and illuminates clouds of dust and gas around the star in an expanding ring, visible from Earth. Visible from Earth as a slowly growing circle of light years after the original explosion has faded. The light that illuminates the ring left the star slightly later than the direct light that arrived first. It travelled outward, hit the dust cloud, reflected toward us on a longer path, arriving years after the original event, as though the explosion were still happening. You can watch old light catch up with old dust and make new illumination in something that ended long ago. The universe keeps finding ways to make the past visible. It does this with everything. The fossil record is a light echo of evolution. Cosmic microwave background is a light echo of the Big Bang. The heavy elements in your body are a light echo of stellar deaths that occurred before the solar system formed. The universe does not throw anything away. It transforms and scatters and redistributes, but the information, the history, the record of what happened persists in some form, somewhere, in the structure of what remains. Nothing that has ever happened in the universe has been lost. It has only moved. Cosmic web is the largest thing that exists. Larger than galaxies, larger than galaxy clusters, larger than superclusters. It is the structure of the universe itself. A network of dark matter filaments stretching across hundreds of millions of light years, galaxies clustered along the filaments like beads on wire, and vast empty regions between them called voids, where almost nothing lives. Voids are not empty in the absolute sense. There are stray galaxies in them, the occasional lonely star, thin wash of the intergalactic medium. But compared to the filaments, they are as close to nothing as the universe produces on large scales. Some voids are 300 million light years across. Regions of space so underdense that if you lived in a galaxy inside one, your night sky would contain far fewer galaxies than ours does. The universe would look emptier, lonelier. The nearest galactic neighbour might be tens of millions of light years further than our nearest neighbours are from us. Our galaxy sits in a relatively rich neighbourhood. The Virgo supercluster, of which the Milky Way is a small part, contains thousands of galaxies in a region about 110 million light years across, and the Virgo supercluster is itself part of a larger structure called Laniakea, a supercluster of superclusters, basin of gravitational attraction, containing roughly 100,000 galaxies and spanning 500 million light years. The name was given by astronomers, those who mapped the large-scale velocity, flows of galaxies in our region, and found that all of them, including ours, flowing toward the same gravitational basin. Laniakea means immeasurable heaven in Hawaiian. The astronomers who named it chose carefully. We are on the outskirts of Laniakea, near the edge of the basin, far from the densest region, in a quiet arm of an average galaxy, in a modest cluster, the address of everything you have ever known. Somewhere much closer, in the molecular clouds of the Orion Nebula, visible to the naked eye on a clear night as a faint smudge below the belt of Orion, though the eye sees only the brightest part of a structure far larger. Stars are being born right now. The nebula is a stellar nursery, a cloud of gas and dust about 24 light-years across, where gravity is slowly winning against the pressure of the gas in dozens of locations simultaneously, pulling material together into the dense, hot cores that will eventually ignite as new stars. Some of those stars already burn at the centre of the nebula, young and hot and blue-white, their radiation blowing the surrounding gas outward in a process that both sculpts the nebula into its dramatic shapes and eventually disperses the material that could have made more stars. New stars destroying the conditions for their own siblings, the nursery illuminated by its own first children. In the Hubble Space Telescope's famous image of the Eagle Nebula, the pillars of creation, enormous columns of gas and dust, some of them several light years tall, stand in the process of being slowly eroded by the radiation of nearby young stars. Inside the pillars, sheltered by the dense gas, new stars are forming. The pillars are being destroyed from the outside while creating from the inside, simultaneously, in a process that has been ongoing for millions of years, and will continue until the pillars are gone. The image became iconic, not because it was the most scientifically significant thing Hubble photographed, but because it looked like something the imagination would produce if asked to draw the origin of stars. Enormous, dark at the base, glowing at the edges, things being made inside things being unmade. The universe is always doing both at once. The formation of our own solar system 4.5 billion years ago was a version of the same process. A molecular cloud, disturbed perhaps by a nearby supernova, began to collapse. The centre grew dense and hot. The surrounding material, rather than falling straight in, began to rotate. The way water rotates as it drains, conserving angular momentum, and flattened into a disk. In the centre, the proto-sun gathered most of the mass. In the disk, smaller concentrations began to grow. Dust grains stuck to other dust grains. Pebbles accumulated into boulders, boulders collided, and sometimes merged and sometimes shattered, and survivors grew larger still, sweeping their orbits clear, and in a few tens of millions of years, fast by any cosmic standard. The solar system had assembled its basic architecture. The early solar system was violent. The planet we now live on was struck, roughly 50 million years after its formation, by a Mars-sized body that some scientists call Theia. The impact was not a glancing blow, but a near head-on collision, and it was catastrophic. Proto-Earth was largely vaporized and reformed from the debris. Much of the impacting body merged with it. Ring of molten material spread around the resulting larger planet. And from that ring, within perhaps 1,000 years, the Moon assembled. The Moon is literally a piece of the collision that made the Earth. Its composition is similar enough to Earth's mantle to confirm this. and its large size relative to the planet. The Moon is unusually large for a satellite of a rocky planet, is consistent with this origin. The Moon stabilizes Earth's axial tilt. Without the Moon's gravitational steadying influence, Earth's axial tilt would varicotically millions of years, shifting the climate dramatically, making the long periods of stable climate that seem to have been necessary for complex life to evolve and persist unlikely. The collision that nearly destroyed the proto-Earth also created the conditions for life. The disaster was also the gift boost. This is a pattern the universe returns to regularly. The event that looks like an ending becoming the precondition for what comes after, the late heavy bombardment. A period roughly 4 billion years ago when the solar system's orbital dynamics shifted and a wave of asteroids and comets rained down on the inner planets, scarred the Moon's surface with the craters we can still see today. The Earth was bombarded too. Erosion and plate tectonics have erased the record. This period of intense bombardment may have delivered to Earth a significant portion of its water, carried in comets and water-rich asteroids from the outer solar system, arriving in impacts that would have been globally catastrophic, but that collectively assembled the oceans. The water you are made of, the water in every ocean, may have come from the outer solar system. It may have travelled in from beyond the asteroid belt in a period of cosmic violence that lasted hundreds of millions of years. And it settled here and remained here. Eventually it became the medium in which chemistry became biology. The oceans are old. The oldest confirmed ocean sediments date to about 3.5 billion years ago. But there is isotopic evidence suggesting liquid water on Earth's surface as far back as 4.5 billion years, almost immediately after the planet formed. Water has been here for most of Earth's history. It has been cycling through the hydrological system, evaporating and falling and flowing, for so long that every molecule of water on the planet has cycled through the atmosphere, through living organisms, through the ocean, through ice, and back to liquid, an incalculable number of times. Water you drink has been drunk before. Many times by things very different from you, in a world very different from this one. Time moves differently near massive objects. This is not an analogy or a metaphor. It is a measured, confirmed feature of reality. Clock, placed near a massive object, runs slower than a clock far from the same object. Difference on Earth's surface versus orbit is small but real and must be corrected for in GPS satellites, which run fast by about 38 microseconds per day compared to clocks on the surface. If uncorrected, this difference would cause GPS systems to accumulate position errors of several kilometers per day. The correction is applied constantly, invisibly, every time a navigation system works correctly anywhere on Earth. General relativity is not abstract physics. It is built into the infrastructure of modern life, corrected for every day, taken for granted in every map application on every phone. Near a black hole, time dilation becomes extreme. At the event horizon itself, time stops entirely from the perspective of a distant observer. An object falling in appears from outside to slow and freeze and redden as it approaches the horizon, never quite reaching it. Stretched thin by tidal forces, proud, its light shifting to longer and longer wavelengths until it fades below detection. From the perspective of the infalling object, nothing strange happens at the horizon. It crosses without sensation, the crossing point, unremarkable from the inside. Strangeness is in what comes after, in the region beyond the horizon, where the destination isn't not a place, but a time. The singularity is not somewhere you can avoid by steering around it. It is in the future. It is where time leads inside a black hole. There is no trajectory that avoids it once the horizon is crossed. Physicists are careful to say that the mathematics breaks down at the singularity. The equations produce infinities there, which in physics means the theory is telling you it has reached its own limits. What actually happens at the singularity, if anything, is outside what current physics can describe. It is the edge of the map. Beyond this point, the chart reads unknown, not because nothing is there, but because the instruments we have do not reach. There is something quietly comforting about the edges of the map. Not the fear of what might be there, the honesty of it, the willingness to say we have gone as far as current understanding takes us, and the territory continues. Science is the only human enterprise that marks its own boundaries accurately. That acknowledges the edges and points past them as the next direction to travel. The universe is about 13.8 billion years old. It will not always be as it is. In the very long future, timescales so large they require scientific notation to write. The universe will change in ways that make its current state look like a brief bright morning. Stars will finish forming in roughly 100 trillion years, when the gas clouds that make them are exhausted. After that, no new stars. The existing ones will burn through their fuel, one by one over the following trillions of years. The massive ones first, then the medium ones, then the small ones, until only the red dwarfs remain, burning their slow, careful fires into the deep future. Then they too will cool. White dwarfs will dot the dark where galaxies used to blaze. Black holes will grow slowly through absorption, and will eventually, timescales of 10 to the 67th power years or more, evaporate through Hawking radiation, slowly, imperceptibly, losing mass in particles created at their event horizons until they are gone. Stephen Hawking predicted this process mathematically in 1974. Black hole slowly radiates. It takes longer than the current age of the universe many times over, for all but the smallest black holes, but it happens. Even the most massive objects in the universe are not permanent. Even the darkest things eventually give off a little light, slowly at the edges, until they are gone. There is something in that which takes a moment to land. The universe in its far future will be darker, colder, quieter than it is now. The stars that fill the night sky tonight, each one burning with the same nuclear fire that produces the warmth of days, represent a phase of cosmic history that has a beginning and an end. We are inside that phase. We are alive in the era of stars, the stelliferous era, which runs from roughly 10 million years after the Big Bang to roughly 100 trillion years from now. In cosmic terms, it is not a brief era, but it is an era. It has a shape. It has a before and an after. We are in the middle of it, roughly. The universe is in its star-making, galaxy-building, life-permitting prime. And here, in this particular middle moment, something arranged itself on a small, rocky planet to wonder about the whole of it. The night outside is the same night that has held every human being who ever looked up and felt something move in them that they could not name. The same darkness The same stars, or nearly. A few have changed, some have been born, a few have died, but the constellations your ancestors named are recognisably the same ones overhead tonight. Orion still stands. The Pleiades still cluster, Gilgi. The Milky Way still makes its pale road across the sky, when the lights below it are dim enough to let it through. Every civilization that has ever existed on this planet looked at those same lights and made stories. The stories are different. Physics turns out to be the same. What the ancient observers felt when they looked up, that specific quality of attention the night sky requires, something between reverence and curiosity and the pleasant unease of scale, that feeling is not separate from the science. It is the beginning of the science. It is what the science grew from and what it keeps returning to when the equations are done and the papers are written and the scientists go outside at night and look up. The feeling is accurate. It is telling you something true. The universe is as large and as old and as strange and as beautiful as the feeling suggests. The math confirms it. The measurements confirm it. The light that arrives tonight from distances you cannot hold in your mind confirms it. It is very late now. The journey has been long, across the solar system and the galaxy, and the deep cosmological structure of space itself, and arrived here, at this quiet hour, with all of that still somehow present. The way a long journey leaves something in you, even after you have stopped moving. Questions that were opened earlier in this journey are beginning to find their quiet shape. Not answers exactly, but a sense that the questions themselves are the right ones. That wondering about the ocean under Europa's ice, wondering about the WOW signal, and whether anyone ever sent it again from wherever it came from, wondering about what exists beyond the observable universe, and what the singularity inside a black hole actually contains. These are not frustrating unknowns. They are invitations. They are the universe handing you the next thread, the next reason to come back, the next night to lie in the dark and let the mind move outward. The stars do not need you to be awake to keep burning. They will be there whether you are watching or not. Patient and constant, their light crossing the years toward you in every direction. The night is deep. The galaxy is turning. Somewhere 50,000 light years away, a magnetar is cooling by degrees too small to name. Somewhere in the dark between here and Jupiter, the Europa Clipper is moving. Instruments quiet, waiting for the years to close the distance between here and a moon with an ocean in it. Somewhere a gravitational wave from a merger that happened before the Earth existed is passing through this room right now, too small to feel, distorting the space between your hand and the wall by less than the width of a proton, and then moving on. The universe is passing through you. It always has been. Dark is complete now. The journey has come a long way. There is a star in the constellation Bootis called Arcturus. It is one of the brightest stars in the northern sky, orange and old, a red giant burning, about 37 light years from here. Old enough that when it formed, the galaxy looked different. The spiral arms were in different positions. The sun did not yet exist. Arcturus is a visitor from the early galaxy, moving through the disk on an orbit inclined to the plane of the Milky Way, passing through rather than belonging to it. A traveller from an older time drifting through a neighbourhood that was built after it was born. Its light is warm-coloured. Orange, the way a coal is orange when the fire has settled. There is something in that colour, in that particular quality of ancient light, that the eye recognises as different from the blue-white glare of young, hot stars. Age has a colour. Stars it reads as red and orange, the cooler end of the spectrum, the ember end. A star cooling toward its long conclusion, still burning, still crossing the galaxies, still sending light in every direction, including here. 37 years ago, the light arriving from Arcturus tonight left that star. It travelled across empty space, found this planet, found your side of it, Voyager 1 spacecraft, out past the heliopause, now still transmits. Its signal takes over 22 hours to reach Earth, whisper from the edge of the solar system. Sent by a machine the size of a small car, powered by the decay of plutonium, still functional, after nearly 50 years in the cold. The scientists who built it are old now. Some have died. The spacecraft they made was still going, back, still talking, still sending back measurements of the particle environment at the boundary between the sun's domain and interstellar space. It will run out of power in the next few years. The transmissions will stop, but it will keep moving. It will cross the galaxy over timescales that have no human reference. In 40,000 years, it will make its closest approach to another star, dim red dwarf. It will pass at a distance that, in stellar terms, is still very far. It will not slow down. It will keep going into the dark. Something made by human hands will be moving through interstellar space long after the sun has become a white dwarf, long after everything on this planet has run its course. The Voyager Golden Record travels with it, gold-plated copper disc, carrying sounds and images from Earth. Music, greetings in 55 languages, the sounds of rain and surf and wind, mother's first words to a newborn child, the sound of a pulsar, mathematics expressed in binary. Encoded on metal, sent into the dark on the chance that something might find it. Carl Sagan, who helped design the record, described it as a message in a bottle cast into the cosmic ocean. The bottle is moving. It has been moving for 50 years. In the timescales of the galaxy, it has barely left the shore. But it left. That is the part that matters. Something on this planet decided to say, "Here we are," and put the saying on metal and sent it into the dark at 60,000 kilometers per hour toward no particular destination. The universe received it without comment. And the record keeps travelling, and the music encoded on it. Chuck Berry's Johnny B. Good, Beethoven's Fifth, a Pygmy women's initiation song, Azerbaijani bagpipes, a Navajo night chant. All of it moving through the interstellar medium in the outer solar system, cold and dark and safe in its metal jacket, carrying the sound of everything the planet thought to include. The stars are the same stars the record passes among. The same ones above you now. The universe has no preference for wakefulness. It does not require your attention to continue. The pulsars tick without audience. The nebulae collapse toward their next generation of stars in a silence. No instrument fully captures. The cosmic microwave background washes through everything at all hours. The oldest warmth there is, too faint to feel and too pervasive to escape. You are inside it. Always inside it. The background radiation passes through this room, through the walls, through you. Ancient light, cooled to almost nothing, still moving, still. still everywhere, still the remnant of the moment the universe became transparent enough for light to travel freely, still here. The day that is over was made of the same physics as everything else, the same forces that hold galaxies in their filaments held the day together. The same particles that make stars made everything you touched. The night continues. Somewhere in the Orion Nebula, a protostar is gathering mass in the dark of a molecular cloud, the gas heating slowly toward the temperature at which hydrogen fuses, a process that will take another 100,000 years, patient and inevitable. The new star does not know it is becoming a star. It is simply following the rules. Gravity pulling inward, pressure building, math proceeding toward its conclusion. Everything proceeds toward its conclusion at its own pace. The Andromeda Galaxy is moving toward us, been moving toward us for billions of years. In the very deep sky, in the constellation it shares its name with, it is visible on dark nights as a faint elongated smudge, 4 times the width of the full moon, but too dim for most city skies to reveal. It is there, 2.5 million light-years away. The light arriving from it now left before modern humans existed. Before any human existed, it crossed 2.5 million years of space to arrive at this night, at this sky, at this particular darkness. 2.5 million years of travel. Arriving now, the mind that can hold that fact and feel something from it is not separate from the universe. It is the universe in one of its arrangements, feeling something about itself. This is not poetry applied to science. Post. It is the conclusion the science keeps reaching when followed far enough. The atoms that think and feel were forged in the same fires as the atoms that burn in distant stars. The difference is arrangement. The difference is time. Given enough of both, matter becomes curious. It looks up. It measures, lies in the dark, and wonders where it came from, and what it is part of, and it is part of all of this. The night holds everything quietly. The galaxy turns on its long axis. The universe expands by distances too small for any instrument to catch in a single moment, but real, cumulative, the space between things growing at the rate dark energy permits. The breathing of sleep and the drift of galaxies are not so different in their patience. Both are movements too slow to watch, accumulating over time into something that was always going to happen, dark as full and deep and very old. Rest now inside the oldest thing there is. The universe has been here through every night that has ever existed on this planet, and it will be here through every night that follows, stars burning at their steady rates, its ancient light still crossing the years toward you, its questions still open, still waiting, still patient. There is more to find. Tomorrow night, when the dark comes again, the journey continues, deeper into the spiral arms, toward the first light, after the Big Bang, into the extraordinary strangeness of what the universe was before it became what it is. It is all still there. It has been waiting the whole time, and it will wait as long as it takes. The stars are still on. The record is still moving. The ocean under the ice is still dark and warm and full of its own patient chemistry. Sleep now. Nah, the universe will keep.